All right, part 3 of the epic video series for the unit circle and trigonometric graphs. There are a few things, so we've looked at where the graphs came from and what they look like. There's my sine curve, there's my cosine curve, plotting the x-coordinate as the angle increases, sine curve plotting the y-coordinate as the angle changes. A few things I haven't mentioned. Some definitions here. Amplitude is the difference between the min and the maximum and minimum value. So the amplitude of a trigonometric function is that distance there. That's called the amplitude. So the amplitude for a sine and a cosine curve in its just standard form, y equals sine x or y equals cosine x, that's y equals sine x there if I start with my axis there. The amplitude is how far above and below that median value it goes, and I haven't drawn that one very well, but we know that it goes between -1 and 1. So the amplitude is that thing right there. Some of you might be into your music and they're talking about amps and the amplifier, and what the amplifier does is it increases the amplitude. Makes things louder basically. The period of a graph is how long it takes until it repeats. You heard me call these things periodic functions because they repeat the same pattern periodically. I could continue that in either direction for as long as I want. I believe I have over here, hopefully, no, maybe not. Where is it? There it is. Here's an example of a y equals cosine x. That's starting at the top because at 0 degrees on my unit circle, at 0 degrees, I'm the furthest right, so the x-coordinate is 1, and it decreases, and it increases back to 1 once we've done a full revolution. Well, that keeps going and going as I go round and round the circle, the pattern repeats. And so it's a periodic function because it repeats itself. The length of a period is the difference between when the cycle starts and when it starts repeating. So if I'm measuring in degrees, a period is going to be 360 degrees, because it's 360 degrees until we start the cycle again. I might even snip one of those out and put that into our OneNote. Why don't I do that? That would be a sensible idea, chewers. Now, sometimes it doesn't like me posting things, and other times it doesn't mind it. Looks like it's going to behave for a change. There we go. So I could start from here and finish there. That would be one period, which in its standard form is 360 degrees. And that, just make a note, that's y equals cosine of x, in case you didn't already know that, but of course you did. We talked about the fact that they're symmetrical. We'll talk about amplitude and period a little bit more as we look at how we can transform these graphs, because obviously when I've mentioned that we can model these, we can use these to model various situations like temperature and tide heights and, you know, sunrise, sunset and all those sorts of things. Well, those things aren't things that vary between 1 and -1. We don't have a tide height of -1. So we can look at how we transform just your standard function y equals sine x or y equals cosine x, changing coefficients, adding things, subtracting things. That's how we can transform these graphs to get them to model situations. But I haven't done the work examples, and I thought I'd better run through those with you just in case you needed a bit of an extra hand with those. So use this graph of cosine theta to estimate the value of theta, of cosine theta, for theta equals 200. Now I'm going to zoom in a little bit there. Hopefully that'll make it a little bit clearer for you. So what do? Well, we go across to 200 degrees. There's 180. These are going up in 30-degree things, so an extra 20 degrees will be about there. Oh, I'm way down here. Now what is that value about there? Well, we're estimating. I reckon it looks like it's about 0.9-ish. I think if you're checking on your calculator, it might be about 0.93. We can't estimate very accurately, can we? If I wanted to estimate more accurately, I could draw it on a larger scale, have more accurate graph paper with intervals labelled there, and you could actually use a graph to calculate all your sine and cosine rather than having to push buttons on your calculator, and it would be accurate enough for us to use. For now, we'll just go along with, we can use this to get approximately the right answer. Find the two values of theta for which cosine of theta equals 0.7. Well, where's 0.7 going to be? That's 1/3, that's 2/3. 0.7's just above there. So at that height, there must be one angle there and another angle over here somewhere. Well, what does that look like? That's 90, 45. I don't know, I'm going to guess about 55 degrees. How would I actually find that out? Arc cos is the way we do the inverse cosine function. We're going to see that soon, but not yet. But arc cos of 0.7, what is that equal to? That's basically telling me what angle do I need, what angle does a cosine ratio of 0.7 represent? Oh, there you go. It's about 45.57. So I'm not a very good estimator there, am I? Or maybe I'm just not very good at estimating 0.7. But it's telling me 45.6-ish degrees. So again, you can see estimation skills not really great when it comes to doing these sorts of calculations. So that's why we use our calculators to give us values. There are other ways they can find them out. I used to have to look them up in a table back when I was at school. You guys are lucky to have the calculators to use. But that's how we go about estimating these values. What's interesting to note is we can also do this from our unit circle. Because I really want you to be able to relate everything back to the unit circle. So this is my cosine axis, isn't it? On the x-axis, I read the cosine value. So if you think about that as your cosine axis and this is your sine axis, it's not a bad way to think about things. So at 200 degrees, I'm going to go around 180, 190, 200 degrees. What is my x coordinate there? Well, you can see that if this is negative one way out here and that's one there, that must be about 0.9. Negative 0.9. I didn't write the negative in there, did I? I said it, I think, but I didn't write it. Negative 0.9, because that's where we're at. What about when cosine is equal to 0.7? So 0.7, I'm probably going to draw it, I don't know, about there. There are two values. One point on the circumference is there, where it's going to have an x-coordinate of about 0.7, and there's another point down there, where it's got an x-coordinate again of 0.7. So we're expecting a number in the first quadrant and in the fourth quadrant. Can you see how, if I break my graph up into the quadrants, here we've got first, second, third, fourth quadrant. You can see how the two values that were at 0.7 occur as expected in the first and the fourth quadrant. So you can estimate those values from your unit circle just as easily as you can from the trig graph. There's a couple there for you to try. What do you get when you estimate the value of cosine theta if theta is 100? Go there on your calculator, have an on your graph and have an estimate. Think about your unit circle, 100 degrees. Oh, I'm just a little bit past 90. What would that be? It's probably going to be a smallish negative number, isn't it? Do the same thing. If cosine is negative 0.6, what two angles is that going to correspond to? I'll leave you to check those answers. Can we do the same thing with sine theta? Of course we can. Now, I'm not going to print out a graph or anything. I'm just going to freehand sketch one here. That looks good enough for me to use. It's roughly symmetrical. There's my y equals sine x. I know that the period's 360, so that's how long it's going to take to repeat. I might put in those other values, 90, 180, 270. That'll give me a little bit of an idea. Is the sine of 70 degrees less than the sine of 130? Well, if I just went back in 10 degree increments from 90, 80, 70, sine of 70 is going to be about there. What about 130? 90, 100, 110, 120, 130. It's going to be a little bit lower, I think I'm going to find. It's 50 degrees from 180, so it's closer to halfway than this one. 70 was closer to 90 degrees, so I'm expecting it to be a little bit higher. I think, again, your unit circle is probably almost an easier way of telling this, because we just look at the reference angle. 70 degrees is going to be that thing there. 130 degrees, well, it's going to be 50 degrees away from the closest x-axis instead of 70. So you can see when I'm looking at the y-coordinate, the sine of 70 degrees is that point there. It's definitely going to be greater than the sine of 130 degrees. So what do we think about this statement? I would say that's false. I would expect the sine of 70 to be greater than the sine of 130. What about the next two? Sine of 195. So 180, 195, it's another 15 degrees that way. Maybe about there. 335. Well, that's 25 degrees away, so it's a little bit further away. So I'm thinking that point here, that's about sine 195 if I trace that back to there. And if I trace this point back to the y-coordinate, that's closer to the sine of 335. So is the sine of 195 greater than the sine of 335? Well, the magnitude is less. It's a smaller vertical distance, but because I'm looking at negative numbers, a smaller negative number is larger than a big negative number. So in that case, I would say yes, it's true. There's a couple there for you to try. Oh, I should say, can we do that on our unit circle again? Well, where's 195? I go 15 degrees around. I'm looking at the sine, so it's the y-coordinate there. 335, well, that's 25 degrees around the sine. Yeah, it's going to be a little bit larger in the negative direction, so therefore smaller than sine 195. There's a couple there for you to try. That's just giving you an idea about how to read them off the graph. What I'd encourage you to do, though, try and look at them on your unit circle and think about it that way too. Your unit circle, it's your best friend in maths. It has all of the answers to your trigonometry contained within it. You've just got to get to know it so that you understand it. I hope that helps. I'm expecting questions in the collaboration space. Good to see that people have started using it. Please continue to put questions in there. If it's hard to ask in there, put something in Teams. Let us know you need a hand. We're here to help. Keep up the good work. This is a fun and exciting bit of maths. It's really powerful. We're going to be able to do lots of good things with it. We've just got to get our heads around it first. Thanks, guys. Catch you later.